Uh, Hey guys, we have been doing this stone game series from the past 2 weeks, and we have covered almost 7 problems. So this is the eighth and the last in that series, and this is almost you could say min-max game or normal DP also you can say, not that typical min-max. So this is our last problem. Let's take it, and then we'll jump to our jump series. And feel free to chime in or add any inputs or anyone if you want to share anything. Feel free to do. Okay, start with this, right? So this question says that like Alice and Bob takes turns on playing a game with Alice starting the first, and there are 10 stones arranged in a row, and on each player's turn, the number of stones is more than one. They'll do the following things. If you find that the integer is, access to be greater, it's not valid for one stone. You remove the leftmost 10 stones from the row and add some of the removed stones. This value will be added to the player's score, and you have to place a new stone whose value will be equal to the sum of the stones that you have removed from the left side. And even the game will stop like when you are left with one stone, and the difference between the Alice and Bob is Alice score minus Bob score, and Alice goal is to maximize the score difference and Bob goal is to minimize the difference. So you are given an integer array of length n, where stones of I represents the value of ith stone from the left. Return the score difference between Alice and Bob if they do optimally, right? Okay, that's sort of right. The chat. Okay, so this is the stone array that is given to you, right? So what the first turn, what Alice is doing is picking the first 4 stones. When you pick first 4 stones, you get a score of 2, right? She get a score of 2, which is added to this, and now she is left with now the turns comes for the Bob, and Bob is left with 2 and -5, right? And the score that Bob obtains is -3, and this is the difference of the score that you'll get 2 because of first, and this is the remaining because of the stones. So it's like first player will go from this side, and the next player will always pick the stone on the right side, including the whatever score that has been obtained by the Alice. The first player. And the same you can see here, like 7 stones. They are picking the. If you pick the entire stone, right, then Alice will give a positive score of 13. Whereas Bob will be left with 0 stones, so score obtained is 30. This is another example.
Yeah, so it's not clear. Like, are they just picking one stone in their turns, or any number?
Any number you can pick, but the problem is that it's both positive and negative number, right? Say, had it been only positive, what will happen? You will pick all the stones and you will win the match. But there is a chance that Bob will have 0 and you might go for a negative score, right? You got my point. That's why you can't pick the entire stones. Let's say,
I'm sorry.
At the test case with 1, 2.
Yeah, I did not understand the question.
My question is.
1, 2, 3, sure, go ahead.
It's like your voice also breaks sometimes, Maybe.
Is it fine now?
Yeah, it is.
Is it fine?
Okay, but sometimes there is a lot of lag. Yeah.
Okay, it looks like because of the network issue.
Okay. So the rule said that they have to choose an integer greater than 1, right? So I figured that the negative numbers were more indicating to the position of the stones in the array, right? Because it says to grab the leftmost stone. So it would be an index of negative value, right?
Mm-hmm. Yeah.
I don't think that it's negative valued stones, right? Or at the very least, a negative amount of stones.
But don't think it practically, right? This is this amount that they are showing in the year, right? You can, what is this? Okay, negative score you will have, right? So don't think it practical that, scores will be negative. It was negative value was added to your score.
No, so is the question that I'll keep on picking up stones until my total score is more than 1, like positive? Like, what is the motive?
No. Scores need not be positive. The game will end only when you have single stone left in your array.
So just to clarify, if I understood the question correctly, you have to pick the leftmost stone that has a value greater than 1 for the first constraint. Second constraint is you are also trying, if you're Alice, you're also trying to maximize the score difference. So here in this example one,
Yeah.
you could have picked the stone with value 2, but instead you picked stone with value 4 because it is giving you more.
No, 4 stones we are picking, not value 4.
You will take any prefix of the array and pick it, right?
Yes, prefix of the array will pick it. And the other stone will pick on the right side of that prefix, not the left side.
No, but when we say any prefix, does it mean like well, like how would Alice choose whether have to pick 1, 2, 3, 4 or all of them, like, or just all
If
but
you pick-
one?
You have
See,
to
all
pick
of them-
all that are a prefix.
See,
You have
all-
to pick all of them.
Let us walk through one more example, if you don't mind.
Sure.
Can
See,
you
what
just
I'm
clear
saying,
this?
what you
whatever
can't pick.
Yeah, and
But
also can we
yeah.
disable annotation for everyone else?
No, that's not possible, right? Yeah.
Oh,
Yeah. Okay, good.
okay,
Yeah,
that's
Shashank,
possible.
yeah, let's walk through.
Pick the stones because the number, see what the number here is. Had the number been only positive, Alice could have picked the entire stone. What is this? Okay, anything, whatever. So let's say X value opened and the other value was getting 0, right? Because you pick, Alice picks all the stones, the Bob will have 0 value, right? So you won the match.
Guys, I'm seeing a lot of scribbling, blocking the entire thing.
Come again?
No, in the screen,
People
right?
are saying, yeah, there are a lot of some writing on the board and all that. So let
Oh,
us,
this,
Somebody
guys-
keep disturbing.
Yeah.
yeah,
Guys,
can someone in the host actually stop
iPhone is
or kick?
okay. This is iPhone.
I see iPhone
iPhone
something.
is there.
Who is that? iPhone is not there.
I mean, just iPhone
Just
only.
disable annotations you can explain on Google Jamboard or some Excalibur.
I'll explain here in the editor itself. It's okay, no problem.
I think guys the iPhone left already. So like we can continue.
Yeah, I think, yeah.
So
Shashank,
did
you can
someone
share
say
it.
the iPhone was there?
Come again?
iPhone was there, join. Someone he left.
Yeah,
he
yeah.
left.
Yeah, they are saying that. Okay, it's okay. Let's move on, Shashank.
Sure. Yeah. So what I'm saying, you can't pick entire stones because here negative value, right? Let's say had there been only positive values, it would have been good choice. Thus Alice will come and pick all the stones and he'll get a score of 3, 3, 6, 4, 10. There will be no stone for the Bob. So overall, the score is maximized for the Alice. Okay. The Mahi, who is Mahi? He's doing that. But if there are negative values, what will you do? What will happen? If you try to pick the entire stone, there might be a possibility that you will get a negative score and Bob will have a positive one,
Mahi
right?
is there now.
She specifically said, I want to come and see her house. Oh, Nikita, but eventually please clean this room. Now cover
You are disturbing.
I want it to see.
Yeah.
So there is this Mahi 2 names, so we'll have to disable them.
Yeah.
Do you have access? Yeah.
Just disable it, right?
Is using an iPhone to join this meeting a problem? Someone was saying.
Oh, sorry, iPhone. The person name is iPhone.
Actually,
Hey, I'm not able to see who's actually doing this. I can do the disabling if you want me to.
Mahi,
What is something to do with the
Mahi.
iPhone? I joined with iPhone. Is that something creating the problem or?
No,
like
you're
Mahi?
fine actually.
Okay.
I think
Okay.
someone else is doing it.
I can see 2 Mahis. I don't know.
no, they are gone. Only one is there now.
Yeah, just disable annotations for now.
Okay. So the score will be what? A plus B plus
A, B
C.
plus C.
And yeah, this Ash is what the hell is that? I think annotate like disable then last. Yeah. So A plus B plus C, right? Next time, let me remove this.
Guys, we are not able to see anything. Comfortable, like it's almost red. Now we are able to see.
Wait, let me enable waiting lock meeting. Play sound when someone joins. I don't see annotation option to disable.
I think
Okay,
it's in the
anyways.
bottom
Your
bottom of your screen.
See, you
With
see
the
there is
zoom
a BM,
control.
2 BMs now. Actually, one of the BM should be a problem. You
Yeah.
see, there are 2 BMs, right? So one of the BM actually.
Yeah, please speak up so we can know you are legit and we will evict the other one.
Yeah, I think BM done. Okay, go ahead.
Yeah, sure.
Yes. Do
Yeah.
Santosh.
Now turn for the box. Okay, it's puzzle. Let's solve it, right? So
Okay, can I?
Yeah, box comes right. Yeah. So when actually these two stones, the score is this, and the remaining CD is there. Now Bob turns comes, so Bob turn will be it'll pick. I mean, he'll have to pick the stones on the right side of it, along with whatever the prefix he has, right? So these two stones is picking A plus B plus C, and then remaining D comma is there. So I mean, if you write A score was initially A plus B. Then if I take B score was what? A plus B plus C, right? This is Bob's score.
Yeah.
Then similarly, next when the next turn comes, what will happen? Alice will pick this D, right? Then A plus B plus C plus what is it? D you can write here, right? So what you can see this prefix sum is carried to both of them, right? And just to get the difference and just maximize it. That is what they are saying. But this will be like more of a n square solution, and the constraint is like 10 raised to power 5 they have given the length. So it will hit TL. I'll show you the recurrence relation. So this you got right. Any issues in there? The prefix sum is being carried to the other players. Okay.
Okay, so you are saying we have to go for a prefix sum. Okay, and
because
then,
he picked two stone. His score is what? A plus B, right?
Right.
Bob will pick what? These two stones. So Bob's score is also implicitly having the the prefix sum, like A score plus his score. Because Bob is supposed to pick this plus any stones on the right side of this. Right.
Okay.
So then only he can maximize the difference. Sorry, he can minimize the difference. So what will happen? You can run a for loop and then all the those many recursive calls you'll have. Like I'll show you here, right here, recurrence relation. So initially this is the function that let's aggregate in which you pass 1, 2, 3, 4, right? So initially first two stones will be picked. So 3 you picked, and minus what will happen? Whatever you get optimal value from it, you'll subtract it. That will give you the maximized score difference from Alice's perspective, right? Then next call could be like Alice can pick 3 stones, 6 minus this optimal function will go, and whatever value you get the difference and return the max of it. So these many calls will be made at the first level. I mean, this is the first level if you see.
6 comes in just like adding the 3 and picking the next
prefix sum. Yes.
Right. Okay.
And what is this find optimal is doing?
It's a recurrence relation. I mean, every time it will go and find the max score.
Oh, it's just adding all of them?
Yeah, same thing it will do. When these 3 things will go, then again it will do prefix sum over 3.
Prefix sum for all of them. Okay, got it. Okay.
So recursively it will keep on going. This is the first level what I'm saying. Then again, this you can see 3, 3, 4. Again, max of it will do like this. Then 3, 3, 6 you took. Then 3 entire. If you take this, then so from here you can see the recurrence. The equations are repeating, right? I mean, same sum is being calculated again and again. So it's more of a dynamic. I mean, DP problem. You can get the intuition out of it. Makes sense, right?
Yes, because we are
But if you do
compressing
this-
the stone and putting it back in the beginning.
Makes sense, right?
Yes, because we are
But if you do
compressing
this-
the stone and putting it back in the beginning. So it's always a prefix sum only. It doesn't actually matter that we are compressing.
Exactly. It's being carried out to the next level.
Yeah, but the prefix sum array will always be modified, right? Like earlier we have 3, 3, 4, and then now it's going to be 6 and 4.
So that's what, if you notice, in the second line 36, it is exactly the same array that we are looking at. We're just ignoring index 0. If we ignore index 0, prefix sum of 1, 2, 3, 4, so it becomes like 3, 6, and it's exact same as prefix sum above with ignoring the first element. Here we have 1, 3, 6, 10. Here we have 3, 6, 10. So our DP relation is nothing but a suffix of the prefix sum. Now we are only considering from this index onwards. Why? Because the first guy has picked this stone. He's picked these two stones. So
Yeah,
he's
so we
combined
have
this
to have
into
a
one stone.
suffix and a prefix, both two different arrays, right? So that
Yeah,
will
we
be
need a
better way of
prefix
doing it.
sum, and for find optimal, we are passing in a suffix of or an index from which we are starting.
Yeah, we should have an index.
In next iteration, he's having only 6 and 4, so 6 and 10. So within prefix sum, he's ignoring 1 and 3. This is ignored. So I would be like 2 or something. And final recurrence, only 10 is remaining. But it's actually not changing anything. Compressing the stone and putting it back is not making a real change in the prefix sum. Because the next guy will have to pick your entire compressed stone, whether he considers it 1 element or 10 elements.
Okay, but why we have to do a recursion? Can we not do using the prefix? Just go and
here we are assuming that we're picking only 2, right? Direct from this step, it might be optimal to go to this step by picking 3 stones and compressing it. It might be optimal to.
We can avoid this also. I mean, this is correct what you're saying, the brute force, but we can avoid DP here. Directly, you can go from the right side, right? You already have a. You got what I'm saying. This is one way, like I mean, exhaustively you span out all the branches and this year. But what Santosh you are saying, you can see you have to the other player score should be on the right side of it always, right? You already, let's say you got the prefix sum of this entire array. If you give e to the Bob, then the remaining score will be what? For the Alice will be what? This total prefix sum minus this particular stone, right? And just keep on maximizing the difference.
No, but Bob is trying to minimize the difference, so he'll try to pick up the prefix sum for sure, right?
Oh, okay. So because of that, we'll need it won't be a greedy, it will always be a DP. Okay.
Yeah, because we don't know it's optimal to pick 2, 3, 4, 5, how many stones to pick from them.
So all the branches will have.
Okay.
So this is I'm creating a prefix sum here, right? And this base score you consider as a difference. I mean, from Alice perspective, I'm thinking of maximizing the score. So let's say initial the difference is the accumulated sum itself. Now we are walking from the back, right? Now, if you give E stone to the Bob, then what will happen? From that total prefix sum, you need to subtract this value, right? The remaining value, this will go to for the next Alice, right? And whatever, and then just to take the difference between this E and this prefix sum, whatever you have obtained, take the difference of these two and check if it is better than the previous one, just to keep on maximizing it. Right.
Well, this is not the same implementation what you discussed about the
okay. This
one,
is a bottom up basically.
Is it bottom
up?
Bottom up space optimized.
I haven't used it. I mean, this is not the same approach. I haven't implemented this one. Okay. It's just it will hit DLE because of n square. This is what I was saying, the prefix sum approach. Like, since the second player will have to take the score from the right side only, right? Let's say if Alice picks all this stone, the Bob score will be this side. So that's why I've started from the right itself, from the back itself, to start giving scores this to the opponent player, and the remaining total prefix sum minus this you do, then this score will go for the next player, and just take the difference of them at every stage.
Okay.
Right.
Yeah.
This is the top down, you can say. I mean, I calculated the prefix sum. Prefix sum of all the stones, like here, and then there are these two calls what I'm making. If he picks I plus 1th stone, I'm starting from the left side here. If you pick the I plus 1th stone, so the next player will have what? Total prefix sum minus this. Or if I don't pick, then abstract way. And whosoever is maximum, that you keep on going every time, right?
So was this also giving you a daily?
No, this is fine. This is what
should not, right? Yeah, okay.
I
So this is at least following whatever you explained earlier and what the implementation explains, the simulation of the problem explains, right?
Nice.
Or is optimized here. And
I did the same thing. It's kind of.
oh, you want to share? Let's go.
It's quite similar, just with a flag for Bob and Alice.
Oh, turning like whose chance it is, right?
Yes, I put that.
Yeah,
Should I share?
Yeah,
okay,
sure,
make me host.
Okay, let me make you host.
I've enabled participant sharing. You can share now.
Thanks. So prefix sum is generated. Now I have the current index from which I can select the stone and whether I want to maximize or minimize. One player is maximizing and one player is minimizing. So if I've reached the end, then just return the prefix. If it's maximized, it will be positive, otherwise negative. And here, if I'm maximizing, so either I include this in my prefix sum, or I finish my prefix sum at this index, and I let my opponent start his turn from there. So include this in my prefix sum means I won't do anything. I'll skip over to the next index and I'll check whether that could be the optimal ending for my prefix sum. And if it's maximize his turn, it will remain his turn. But if I decide to end my turn over here, okay, I decide that, okay, I will pick up these stones now. This is my X. So then add it to my score, and whatever the opponent does, that is the next part. So plus whatever the opponent does here. And since it's opponent's turn, I just say not maximize. So it flips the bit from true to false. And otherwise, if I'm a minimizer, okay, so either I just continue and see ahead that let the ending point be a little bit in the future. So DP of I plus 1 with the same flag, or else I'm going to end over here. So my score negative since I'm a minimizer plus DP of opponent, whatever the opponent gets from next index onwards. And this is exactly what Shashank did. He just put a minus here, so he didn't have to make minimizer, maximizer separate.
Yeah. You can share this code also in the Discord.
Yeah. Any question?
Yeah, actually. Yeah, so can you walk through on this line 14 and 16? You're
Yeah,
saying,
sure. Yes.
A very quick example. I don't want a very detailed one.
If my prefix, okay, if I want to pick 5 stones. So currently I want to pick 5 stones, 1, 2, 3. And let's say my prefix sum is also stored somewhere 1, 3, and 6. So let us say that it's my turn, okay, and I'm at this particular stone is what I'm watching with current turn. So now I have 2 choices: end my prefix sum over here, which means add this to my score. This is prefix I, and then give the turn to my opponent for the remaining suffix. So I plus 1 and flip the bit. Okay, this is one choice. This is fine. This part of the statement.
Okay, yeah.
Yeah. Now, if I choose not to end my turn here, I go and it's my turn and I'm considering ending it at the next position. So just DP of I plus 1 with the same flag.
Okay.
Consider ending it here. So it's like a knapsack kind of. At each point, I consider either I end over here or I don't end.
It's like a cadence algorithm.
Yeah.
Yeah, and in this case, they're all positive. So it kind of seems that we'll always maximize taking the whole array, but there can be negative. So that's why we are comparing whether put like kind of including it will make sense or not, like will maximize or not?
Yes, yes. Whether I end here or whether I end here, every ending will
Uh-huh.
get tried because it will get called
Got it,
deeply
yeah.
recursively.
Mm-hmm.
Okay.
So these are the two choices Alice has. Either I end my picking over here, I pick this prefix, or I continue to check whether picking the next prefix is better. And if I end over here, the remaining part is for Bob from I+1. If I don't end from here, then again from I+1, I can try to end over there. And when I'm ending, I'm adding the prefix of the entire array.
Okay. But then when you come on 16, you actually do a minus for that particular prefix.
Yes. Since Bob's score is negative, so he wants the most negative answer possible, which is minimum. Bob has a negative contribution to the result. Bob's is a negative contribution. Alice is a positive contribution.
Oh, okay. That is the reason you do negative.
Yes,
sorry, I
that's
didn't
the
follow
logic.
that. Okay.
Score a difference. So I just did it like this. But of course, you can do it in without the flag, how he did it. Calculate the difference on the fly and return the difference.
Yeah, now it is clear. Yeah, sure.
Yeah, okay.
Yeah,
I'll stop.
thank you. Yeah,
thank you.
Thanks. Yeah.
So I think we are done with almost all the stone game, right? Whatever was there.
Yeah, but you were showing the last, the most optimized version of your implementation, right? So can we go there and yeah. So now here,
Go ahead.
let's go through this, the optimized version, because you have completed the previous top down, correct?
Yeah.
Okay. So now in this case, so you are not using, or you are doing that negative on line 8. Okay.
Yes, this is like opponent score you are getting. If Bob selects the last stone, then remaining score will go with that array. Okay. Yeah, if you look at this array, you already have a prefix sum, right? Let's say you give -5 to the Bob. Then for Alice, it will be what? Total prefix sum minus this you do, right?
Okay.
And now take the difference of these two, and you have to maximize that difference. So I'm seeing here from the Alice perspective. I'm not, I mean, which will be.
Yeah, makes sense, right? Yeah.
Both it will work, yeah. I mean, whenever you find that you have maximized this difference, right? Let's say next time what will happen? Bob will take these two stones, and out of this accumulated sum, already you have subtracted the 5. Now next time Bob has taken 4, so 4 also you subtract from this, and just now take out the difference of these two. This score minus, sum this score and take the difference, and check the previous difference was better or this. I mean, which one is maximum out of them? So this statement is little bit, what do you say, this one, main crux of this only, right? Alice has to maximize the score difference, and Bob's goal is to minimize the score difference. So both of them will try to maximize the score, then only the difference will be maximum, right? So this is.
So you're basically doing from the reverse, right?
Yeah, from the reverse, backside I'm picking.
Yeah, because you have already accumulated all the values. Okay.
So simply now you need to take care of Bob. Alice will automatically get the complement score. And we are taking care of all the possibilities by giving 1 stone to the Bob, 2 stones to the Bob, 3 stones to the Bob, right? So it's not that we are going greedy way. It's like all the approaches we are, all the exhaustive search we are doing, kind of. All the possibilities.
Well, I still don't understand how you can say exhaustive search we are doing in this implementation. No, right? You already have an accumulated value, and then you're going from behind, and then you're subtracting that, isn't it? So you are just comparing within two values, and then you are reducing one value every time. That is what you are removing that from the accumulated sum. Or am I missing something?
Yeah. No, you are correct, but I'm trying all now. See, initially the Alice score was -5, right? Now next time what I'm giving 4 to him, right? Then next time I'll give -3 to him. So I'm searching all. What do you say? I'm scanning all the possibilities what Bob can have. Isn't it? Or am I missing like?
Yeah, it makes sense the way the implementation is. So, well, for me it looks like very normal greedy solution, maybe. At least looking at this
It's
implementation.
like a bottom-up DP with one result for this.
Because he has just transformed the input now in a different form, and then
Yeah.
he's just going from behind. That is what I'm looking at.
But it's not
Because
greedy. I'm not saying
this
because,
implementation has actually made me bit more confused than what earlier you were explaining, that min max theory, right? It was almost the same for the top down, and also Yuan solution was similar, but only for this implementation slightly it confuses. Yeah.
So it's not greedy because you don't know that at the end you'll have the maximum value of the stone, right? It can be either positive or negative. So on what?
Oh, so you are actually storing that value in the best score, and that is okay. So that will take care of it.
Yeah, every exploring all. Yeah, go ahead.
Yeah. So are we only when we are going in the reverse order, are we only considering one element at a time? That's what I read.
Yes,
or
only one.
Okay, only one, and keep on. Okay, got it.
Shashank, you can share your other one, the DP one above. We can relate it to this.
Yeah, I think the step is -1, right? So
It's the exact same thing. Best score is basically a function of I+1, right? Either you are the same as I+1, so you go backwards. That means you are the same as the previous result, or you are equal to accumulate minus the best score. You can go back there. So either it is accumulate plus best score, or it is best score again. F of n I+1 is equal to best score, right? F of I+1. So f of I is equal to basically best score, or else accumulate minus best score. So it's a DP where you like store the current and the previous, since I depends on I+1. But even that he's doing in one line of the max. So he's just scoring one thing, but f of I.
This is how you do the cadence, right? You local sum you maintain.
Cadence also is actually a DP problem with which we have reduced into that.
Okay. Now
it's the exact same code as the previous slide. Instead of function call, you just write best score.
Yeah.
Since it's initialized to the base case of accumulate sum, and then at each iteration you are finding the next prefix, like prefix of I+1 or I, and then either f of I is equal to max of f of I+1 or accumulate minus f of I+1.
What is the base?
Base case is the entire prefix sum on line 5. In line 5 on this code, and in the other code it's the if condition for max length.
Okay, now I'm getting, like you are saying, it is like a Karan's algorithm, but it is again a modified Karan's. Okay.
Yeah, or it's just a bottom up of the previous recursive.
Yeah, when you call bottom up, actually it is very difficult to follow in some cases, right? Yeah. So this is not even bottom up.
Shashank, can you paste it just below this? Can you paste the recursive solution? You will find the relation.
A question about the base condition. So we are stopping whenever the best score is what we would have got, adding everything.
He goes to the end. He doesn't stop.
Yeah, base case is the last element. So if you see, the for loop starts from second last, and on line 5 he initializes it as. Can you go to put this just below that? This def of f of n, this 3 f of n lines. It's exact same as the for loop, the function. It's a 1-to-1 copy. That function, 24 to 28, you can paste below the for loop, or you can paste the for loop here. We can see it's exact same.
You can actually lower down the resolution, right? Yeah.
So basically here, if you see, the if condition is his line number 5. That is initially the case is that you are equal to the length of stones, like you are the entire array. Okay, that's his if condition. Otherwise, okay, best score, now you keep in mind that it is equal to the previous result of the next previous suffix. So accumulate sum is nothing but our prefix I+1. So now when we return max of these two, we are just initializing that f of I is equal to max of f of I+1, comma, accumulate minus f of I+1. But f of I+1 and f of I both are best score only. On RHS, it is the previous best score, and on LHS, it's the current f of I. On RHS, it's f of I+1. This maps to this. This
Yeah,
one maps
no,
to best
what is
score.
this last
This
line
maps
you
to
said
best score.
about best score? How can 2
Yeah,
be best
these
score?
arrows you can see, these arrows. Best score is initialized initially to the base case. Okay.
That is accumulate, right? The first.
Initialized to the entire sum.
Mhm.
Okay. Then we get the prefix sum at the current index I. So accumulates minus stones I. Entire array minus current. So this is prefix I plus 1. This is prefix I plus 1. Okay. And now we are returning. So that means this is f of I, correct? In the bottom up solution, this is f of I. This is the relation. It's max of the previous result or previous current prefix sum minus previous result. Current prefix sum minus previous result or previous result.
Okay.
It's exact one-to-one mapping to this. Instead of return, he's just set a equal to and made the for loop go to the before I. So now I plus 1, then I. So it's just backwards working on this relation only. It's a bottom-up DP without a. It would be the same as writing an array here f of I equal to
DP of I.
Yeah, max of f of I plus 1, comma, prefix minus f of I plus 1. Why? Because this best score in the previous iteration of for loop was our f of I. And now we have done a minus minus. We have gone back by one level. So it's just a 1D kind of DP, if you prefer to think it deep.
Yeah, now it actually boils down to that. Okay.
It's the exact recursive code
Exactly,
written in this format. But it's very smartly is using one variable to store f of I and f of I plus 1 since RHS LHS.
Yeah, true.
Yeah. So
No problem. Yeah. Thanks, Johan. Thanks, Shashank. Yeah, sure.
Okay, now. So let's move to the jump game, right?
Did we do Stone Game 4 in this session?
Yeah, we did.
Okay.
Yeah, you have done, no? Last I have done. Last two.
Yeah. Now we'll start with this jump game. So this is first problem, like you are given an array of non-negative integers and you are initially positioned at the first index of the array. Now each element in the array represents your max jump length at that position. You have to determine whether you are able to reach the last index or not, right? So like when you're at 0, so 2 steps you'll take, you reach 1, and then 1 step you take, you'll reach here, and whatever's index plus 1, if you do, you'll come here, right? So overall you'll reach.
Yeah, I got this in an interview recently.
Oh, yeah, this is commonly asked here. So how do you approach this?
If we just to do brute force at each index, we'll try all the jumps, all the lengths that are possible, and we return whether any of those are possible to be true. So like a recurrence relation. For I, for j in range I comma nums I, like for the first index, I have some options. From here I can jump to 3 or I can jump to 1. From second index, I can jump to 1 or I can jump to 1 or I can jump to 4, right? So my base case is I am last element.
I think they are not asking for the minimum jump the way you are doing.
No, I'm not showing minimum. I'm showing all the options. Brute force exponential time, I'm saying.
Okay.
Yeah. So you just check where in the recursion of I, you go to I plus 1, then you go to I plus 2. If any of this is true, then the answer is true. But we quickly realized that this 1 can be approached from 2 jumps from there or 1 jump from here. So we could convert it into DP. So that would be the second observation. Now, after that, I don't know how to come up with the intuition for the greedy, but
Yeah. So what I thought was. Yeah. So what I thought was that.
Go ahead.
When I was approaching this question, of course, the interviewer hinted a little bit, but then I realized that at every index, right, we don't care about where all we can go. We only care about where max we can go. So at every index, if we can keep on storing the max distance, right, then probably we can know if we can reach the end.
Yes, that is the best. Order
Yeah,
n.
that's the optimal if you realize that. Continuously keep a track of the maximum position you can reach, and at every
Yes.
index you can update it. Keep moving.
Yes. So the way I also started with that okay, from second I can go to either 3 or either 1, but then I soon realized there will be a lot of things to track and take care. Like it was just impossible for me to kind of even think that how you would, like, I thought it will be TLE even if I write that solution.
Yes, it's like a
So-
max comma n
Yeah.
multiplied.
So yeah, so then I was kind of hinted, and then I got to in this direction that we
Even
have
if we
to.
don't come up with the greedy, I think if we are doing a DP, right, we could come up with like we need a range query over the range of jumps, and then we can quickly realize that the ranges are overlapping, and we can just keep track of the end of each range. Like basically in the first index, I want to think that I can do a range query over the next 2. So is any of this true is basically what I want to ask. Any of these elements are true, right? And if I'm pre-computing from right to left,
Yes.
I can do this range query in log n. So then it becomes a n log max. And then of course we can realize that, okay, this range, all these ranges are overlapping. Just keep track of the end of each range. Maximum you can reach.
Yeah,
if you're
that n log max thing, Bjorn, can you explain that again?
Oh, yes, sure. At index, okay, I want to know from I all the way up to
If you're
I
writing
plus,
somewhere, I'm not
yes.
seeing it at least.
Okay.
I
So
think
now
you have
it's
to click
visible.
out of the box to make it visible to other people.
Oh, okay, I see it. Okay, I see it.
Yeah, I think while typing it's not. So this is what we want to know, right?
Yeah.
From I all the way up to that I plus whatever jump is a max allowed at I. We want to know if any of these values are true between this range, right? It's a range query, like from 3. We want to know whether any of these values are true. Okay. At 3, so if my I is equal to 3, from I up to this value of I plus 3. If any of this is true, then I can say that this is true. Correct? Because from that jump, if I can reach the end, means from any of these I can reach the end. This is fine?
Yes.
So now it just becomes a question of querying the range in log n, which we can query easily, right? Range sum is greater than 0, then it's true. Range sum is equal to 0, then it's false.
Johan, can you please repeat again?
Okay. At position 3, okay, I want to know whether I can reach the end. So from 3, I can take up to 3 jumps. So I can go to this index. I can go to this index. I can go to the last index, right?
Yes.
These are my 3 options. Now from any of these indexes, if I can reach the end, okay. So my reach end, let's say that's where I'm storing my answer. Reach end is one array, which I've already filled up to this point, okay. Currently I'm at I. Okay, at 3, I have filled up the array. Now what I need to know is whether among the next 3 elements I have a true or not. That's all I need to know, right? If any of these can reach, that means I can also reach over here.
True.
Right? It's like if I can jump to these 3 guys. These are my jumps. One of them can reach the end, then I can reach the end.
Yeah.
So I can just do a log query of range sum over this. Let's say 0 is false and 1 is true. Right?
Okay.
And this is a logarithmic query. So I set myself as true, then if it's greater than 0, the sum. Then again over here I have a 2. So either I have to find out in the range from here up to here, what is the max I can get? Like what is the value of true or false? Is there any true in this range? So of course this guy's true. So if one of these guys can reach the end, so I can also reach the end. True. Finally, I just need to return reach of 0.
Yeah, so what I'm not able to get is, okay, for what you're doing for 2 makes sense, but what you're doing for 3 with 0, 1 doesn't. Like I thought it will be kind of a recursive that for every kind of a index, I have to
You have
explore
to go to
the
all this,
remaining
right?
ones.
Yes.
Yeah.
But let's say we are
Okay.
doing bottom up. Okay, we're filling the array backwards. So at this 3, I already have the result for all the next guys. Okay. I already have the result for all elements in the suffix.
Got it. So 4, you see that one of them is true. That's why you're gonna, okay.
Yes.
Okay,
So I just do a range
I
query.
got it.
Any of them is true, then I am true.
Yeah,
And
this
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 would-
binary search thing is like that good bad version search.
Oh, okay.
Yeah, that problem. Yeah.
So yeah, because I think the greedy thing about this, if we've not seen, it's quite tricky to come up with. This is what I came up with when I approached.
Okay.
But I had one thought actually. So if you come from the end, right?
Yes.
You start from the end. Like for example, in this case, 2, 3, 1, 1, 4, right?
Right.
If you come from the end and if you just check its neighbor, can I reach 4 from the neighbor? Like in this case, it's 1. You can take one step to reach, right?
Right.
So that means you don't need to worry about 4 because anyway you can reach from 1 to 4. So that is already known now. So now your destination is 1. You can change your destination to 1. Could this be a linear complexity solution?
Yes, that would be going towards the optimal. But if you see one counter example, if there's some example below which returns false, where you cannot reach the end.
Can you give me an example?
Is it that? What's the next example in the question? So you're false, right? Because there's a 0. So let's say from here you can go to this guy, you can go to this guy, you can go to this guy.
So in this case, right? If I come from the end again, well, if you think about the same logic, I'm coming from the right side in this case. So 4, can I reach 4 from the neighbor 0?
Yes, you can.
No, I can't, right? 0.
No.
So
Wait.
that means
you're coming from the right side, So first you will
Yeah.
initialize 4 as true. 4 is the end. So 4 can reach the end, reach end array. Then you come at 0, okay? And 0, there's no range only, so it's false.
You can't reach
Then
because
you come at 1. 1 has a range of this guy. It's all false, so 1 is also false.
That is of order of time n squared complexity, right? Go like that.
No. What I'm saying is, if 4 is the destination, right? 4 is our destination, right? To begin with. So from to 4, can I reach from n-1 from 0? No, I can't reach, right?
Yes.
So directly you will return false.
No. Yes. Then what I will do, I'll proceed and I will check if n-2 can reach n.
Yeah. Okay. So, that is also false.
Yeah.
Okay.
Suppose in this case, I think you wrote it right, 32204. So from 0 I can't reach 4, but from n-2 I can reach 4.
Yes.
Right? So then my new destination would be n-2. I don't need to worry about this 0.
Yeah. So, but when will you return true or false? So if you get
if I somehow pick my destination as 0, then that's my target.
Yeah, you're doing the optimal solution. You're just doing it from right to left. This is the optimal solution. Always keep track of the one that is right now reachable.
Yeah, but this is
linear.
In just a for loop, can we maintain 2 variables? With that, I think we can get it right.
Yes.
So one is just sum of the maximums.
Yeah, you find the new destination at every step. You are finding your new destination for the current destination, and you are making that as current destination. And again, you keep looping that until you reach the first step.
Yes.
And if you reach the first step, then you are done.
Yes. That is order and time complexity.
This is the optimal way to do the problem.
Yeah, brute force would be to explore all the possibilities, right?
Like correct. And then
to 1. And if they ask minimum, you run a BFS or minimum, right? That will give you which is next problem.
And so we are converting brute force into DP, right? Because same is reached from many. So DP of I returns instead of true false, it returns the number of steps.
I just did a linear search. I mean, same like what we have discussed just now. So initially I'm making that whether I can reach or not. It's 0 initially. Now I walk through the index and the number, right? This is the case like if you hit 0, like if you come at this point and you hit a 0, you can't move further, right? So you'll return false in that case. Otherwise, whichever index, let's say if you are at, this is 1th index, 1th index plus 2, so where it will take you to 3. And what is your till now where you have reached, right? You just keep on maximizing your can reach. Like let's say initially you were at this point, right? When you took this one, so to what extent now this can reach will change to what is it? This is what 1th coordinate 1 plus 2, so it will take you to 0. So your can reach will be at this point, right? So every time you update your can reach, just check whether you can cross the length of the array. If so, you return to otherwise false. Right?
Yes.
Is this
It's
greedy?
exactly what we discussed, isn't it?
This is the same thing what we discussed now.
Yeah, greed maximizing every time, right? The can reach.
Yeah.
Johan, I did not get the first way. What you are telling is like you check all the possibilities. That is the thing.
Yes. At each position, you go for for j in range up to the max jump you can do, and check whether any of them reach the result.
Oh, okay.
Base case will be true if you are greater than equal to length.
Okay.
You can go from here to here. You can go from here.
Second optimization is it's a DP problem because you can reach the same space from many different indexes. So you just put a DP on that. Third optimization was that it's a range query. You are just checking whether a range is true or false, right? It's deterministic range that you can jump, continuous interval you can jump in 2, 1, 0. So just check whether any of that is true by doing a bottom-up DP and maintaining a true-false like DP array. And then finally we reached to this greedy one, like we don't need to maintain any range also.
Yeah. So shall we move to next? If no queries here.
I've just got one query from the solution that Prashant suggested. When we go from the last index of the array, there was a suggestion in as an array that 32204, right? So in that case, we were checking that if I can reach to that particular index from the leftmost index I have. If that's 0, okay, I can skip it and move on to the next one and check, okay, is my current destination reachable or not, right? But in that scenario also, when I'm at the second index, that's 2, and I want to check if I can reach from the leftmost index to this current destination, yes or not. But of course I can reach to 2 from 3 as well, right? So we would be checking out all possibilities in that scenario as well, or not?
I think you need to check from the 2 to forward, not backward direction.
In
So
every
here,
step, right?
Yeah.
So in every step.
See, you can do it both ways. A linear scan you can do from right to left or left to right, if path exists, right?
Yeah, but in both the scenarios, we would have to check for all this. Like,
oh, wait. Your jump is from left to right. So when you're on the right, it will be much more tricky what you have to keep track of. Yeah.
So why tricky? It will be simple, right? So here in this
so you are
case,
keeping track of destination, new destination, but
right. Only
you have to keep track of
index. You have to keep only index, nothing else. Okay. So here in case of 4, right? When you 4 always true, right? So keep the index here 4, you keep it from 0, which is index of 3. Okay. From 3 plus 0. Okay. It will be 0. It is not going to reach 4, right? So when you come to 2, so it will be 2 plus 2, right? 2 plus 2 equal to 4. So it is the 4, right? You update the current reachable point is now 2, right? So then come to 2. 2 plus 1 is 3, right? Which is greater than the current index 2, right? So we can
correct.
So you can go like that. So it's fully linear.
My thinking is, if you are in 4, right? If you are at 4, find any previous step from which you can reach 4. I think you can.
Yes, that's what we're doing, and we're doing it greedily. That will find the leftmost step.
Yeah.
Current leftmost step we'll keep track of.
If you find that previous step, right? Any previous step, that is your new destination. You don't need to worry about rest of the array. So in that case, it's kind of linear. You're not repeating your calculations.
Correct. Linear.
Yeah. So Let's move to next then.
Yeah.
This is like another one. So what
I
we are
can
doing
share the
here-
one he explained right now, right to left. So leftmost successful position, this is my new destination. But this is the position on the leftmost, which is true. Then I assume my start position at the end. And my jump power is just my positions of that start position. Now from here, if I can cross the old destination, right, the leftmost success position. So I have enough power to reach. So now this is my overall goal. Now this is my new destination. This is redundant. Yeah. So just keep on updating the leftmost successful position. And at the end, if it is 0, that means your new destination is your 0. So you've reached success.
Oh, so back side you are going from right to left.
Yes, yes. This is right to left, keeping track of the leftmost true, as he explained.
What is line number 21? Keep equal to sign.
So this is now
you reach the
yeah, you reached the start. From the end, you went backwards and you reached the start.
It should be double equal to 3. Yeah,
oh, okay.
So this is just Java.
Oh, JavaScript. Okay, sorry. I thought Python.
Oh, in Java it will equal to means 3 equal.
In JavaScript,
Java
if you
is
write 3
script.
equal, it will check the value as well as the type.
The type, yeah.
Oh,
That's
okay.
very strict checking, yeah.
Oh, okay,
I think so, yeah.
okay.
I wrote this long back.
Johan, one
Good.
question, like in line number 21, you are writing equal to 0. Why it is that?
Okay. So as he explained the method, right, that going right to left. So I also found that I had also done this once. So we are taking track of leftmost true, okay, leftmost successful position. This is our destination, okay. Initially, only the destination is true. Now we assume that the start position is the last position, and we keep going backwards, okay. This is a for loop from right to left. At the current position, what is the maximum jump I can do? Okay, I take that value from that position. Now, if this maximum jump I can do allows me to reach the current destination, the leftmost success, the current destination. If it's greater than equal to means I can reach from here. I have enough power to make this jump to reach the goal. So I update my leftmost destination as the current position. So now this is my destination. Now in the future, I just check whether I have enough power to reach this successful position. If I can reach this, means I can reach the end. And at the end, I just check whether my true value is origin. Like, is origin a successful destination?
That's correct.
You can even go from the beginning also, right? For the start position.
Yeah, the reason is because if you start with DP and brute force and bottom up and all, then that range query, then you might realize that this is the way. Like he intuitively explained it when I was explaining the range query, going from right to left. It's the exact same thing only. It's the same code.
No, but won't it be optimal to go from the beginning? Because
it doesn't matter, no?
You have
it's a for loop.
you
are keeping track of the rightmost position, right? You are keeping track of rightmost position from origin.
No, but what can happen is, like, if you have 4 0 0 0 0 4, can you take that example? 4 0 0 4, like only you can reach last stone by the first stone, right? Let's take this example.
Okay.
4. The first one is 4.
Okay.
Right, 1 2 3, maybe in this case it's 5, right? Because I need 5 jumps to reach.
Okay.
Right, so in this case, if I begin from the start, right, I don't need to even worry about all these middle zeros. And in your case, okay, anyway,
because of the short circuit, yeah.
Even in your case, right, if I put 1 here, can you change it to 1? The last 0 to 1. No, last 0.
Oh, yes.
And this is 4, let it be 4. See, now in this case, what happens if you are coming from the other side, right? You will take individual steps to reach 5.
Correct.
But if you start from right,
by the way, you are not jumping to 5. You are still going to go over these elements only because because there's 5 elements you are jumping, so it's a short circuit. Right. That's what you mean.
Yeah.
That this for loop might get early exit. Yeah, because but otherwise, if this was, let's say, 3, And here there was a
Yeah, so this is very data specific, right? That when the other approach will short circuit and when this will short. I think they're saying
very much on the test case. It's
exactly.
2 of n. It's just that short circuit.
Exactly.
I don't know if we can add here. I don't think so.
In the best cases, you can skip the intermediate steps, is what I'm saying.
Yes,
If
you
start
can.
from,
If this 5 was reaching the end directly, but if it was a 3 and we had 1 here,
yeah, of
so
course.
again
In
our
that case, you have
algorithm
to
would
jump
also go
through.
here,
Yeah.
and then it would come here.
Oh, okay, I get it. So you're saying the
Yeah,
back approach, you'll always have to go because we have to. Okay.
Yes.
Yeah.
Back approach can only update myself as current, but your approach can update yourself as the max term.
Got it. Yeah, makes sense. Okay.
So it will short circuit.
Yeah, I implemented the same thing. It is working fine.
Then the DP and all which I explained, I tried all those. So at my current jump, for every next jump up to my max jump, check if it's true. And return of position 0 DP. And I tried a BFS as well for TLE. At each index, insert all the elements up to my max jump. Yeah, but
yeah.
linear.
BFS is like, yeah, kind of, I think more natural for this because you are, yeah.
Okay, shall we go to next or shall we take it next session? Because we are almost on time, right?
Yeah, next session we can take 3 questions is there remaining.
Yeah.
So this happens on daily basis. Actually, this is the first time.
Let me stop the record. Yeah, go ahead now.